Hello friends, dear learners and my dear student. First of all, I take an opportunity to welcome you at my M.Sc Analytical Chemistry class. Friends, I am Dr. S.R. Labhade, working as Associate Professor in Chemistry at KTChem College, Nashik. Student, in previous lecture we discussed the analytical principle and working of cyclic voltammetry. In addition to this, we discussed the use of cyclic voltammogram for qualitative and quantitative analysis. In today's lecture, we will discuss the use of cyclic voltammetry in the study of reversible and irreversible reaction. In addition to this, we also employ this cyclic voltammogram for determination of N value, that is a number of electrons involved in redox reaction. Therefore, the applications of cyclic voltammetry, number one is qualitative analysis. Qualitative analysis in cyclic voltammetry is also done by using a half-wave potential. Similar to polarization analysis, in cyclic voltammetry, half-wave potential is utilized for identification or estimation of the sample component which undergo oxidation and reduction at working electrode. Therefore, in quantitative analysis, in cyclic voltammetry, the cathodic current is obtained at a potential to which analyte undergo reduction at working electrode, and the anodic current is obtained at a potential to which analyte undergo oxidation. That means these potential corresponding to anodic peak potential and cathodic peak potential, that is EPA and EPE. These are respectively, these potentials are respectively EPC and EPA. That is cathodic peak potential and anodic peak potential. Therefore, in cyclic voltammetry, the potential at the center, or central potential at the center of EPC and EPA is called as a half-wave potential. Similar to polarization, it is represented as even half, which is a identity of analyte species undergo a redox reaction. That means in cyclic voltammetry, we are plotting a graph of here a current in microampere versus a applied EMF. Here this is a IPC. If we are increasing the potential, this is a IPA, and here this is called as EPA and this is called as EPC. At the center of this EPA and EPC, whatever potential we have, that is a half-wave potential. Therefore, this half-wave potential is utilized for identification of electroactive species, and it is determined by using a value of anodic peak potential and cathodic peak potential. Therefore, center of the anodic peak potential and cathodic peak potential is the half-wave potential, and we know that half-wave potential is the identity of a material that undergo a oxidation or reduction reaction at working electrode. Therefore, in cyclic voltammetry, qualitative analysis or identification of analyte species is done on the basis of half-wave potential, and it is determined by using a anodic peak potential and cathodic peak potential in this way. The quantitative analysis, in cyclic voltammetry is done by using a Randles-Sevik equation. In cyclic voltammetry, we know that when analyte undergo oxidation, we observe the anodic current, and when analyte undergo reduction, we observe the cathodic current. The magnitude of anodic current is directly proportional to the amount of analyte that undergo oxidation, and magnitude of cathodic current is directly proportional to the amount of analyte that undergo reduction. Therefore, the cathodic peak current and anodic peak current directly utilized for quantitative determination of the analyte. Therefore, in cyclic voltammetry, the magnitude of anodic current, magnitude of cathodic current is directly proportional to the amount of oxidant that undergo reduction at working electrode. Therefore, here this IPC is directly proportional to concentration of oxidant, or it is given by a Randles-Sevik equation, that is IPC is equal to 2.686 into 10 raised to 5 into n raised to 3 by 2 into d raised to half into a into mu raised to half into concentration of oxidized species or oxidant present in the solution. In this case, this is a constant. Here, this is number of electron involved in reaction. D is a diffusion coefficient of that oxidant. A is electrode area, and mu is the scanning velocity. Similarly, the magnitude of anodic current is obtained during the oxidation of analyte is directly proportional to the amount of reductant that is oxidized, is equal to 2.686 into 10 raised to 5 into n raised to 3 by 2 into d raised to half, but it is for reductant. A area of electrode, mu is scan velocity, and C is concentration of reductant. Now in this case, these equations are called as Randless-Semik equation, and this equation is utilized for determination of concentration of oxidant, that is a species undergo reduction at working electrode if we measure the cathodic current. This equation is utilized for determination of concentration of a reductant if we measure the anodic current, that means species undergo oxidation. In these two equations, that means in Randless-Semik equation, here n is equal to number of electrons involved in redox reaction. Here D is diffusion coefficient for that particular species, measured in square centimeter per second. Again, A is electrode area, that means working electrode area, which is measured in square centimeter. Mu is a scan velocity, that is voltage scan velocity, and which is measured in volt per second. Cx and Cox are the concentration. Cox and Cred are the concentration in millimoles of oxidant and reductant respectively. Oxidant and reductant. Therefore, in cyclic voltammetry, we can determine the concentration of oxidized species or reduced species in forward or in reverse scan by using a magnitude of anodic peak current or a cathodic peak current. Therefore, here we can use this cyclic voltammetry for quantitative analysis. In this way, cyclic voltammetry is used for quantitative analysis of oxidant and reductant. If you observe the Randless-Semik equation, that is IPA is equal to IPA or IPC is equal to 2.686 into n raised to 3 by 2 into d raised to half into A into mu raised to half into concentration of that particular species. In this equation, here 2.686 into 10 raised to 5. In this equation, all these parameters are kept constant for determination of concentration of particular species. Similar to polarizographic analysis, the cyclic voltammetry is also a comparative method. Therefore, peak current directly proportional to concentration of respective species, and we can utilize that particular concentration, particular peak current for determination of concentration. And it is a comparative method, means we have to perform the similar experiment for the standard solution also. Then all other parameters are constant. Current for standard, concentration of standard can be utilized for determination of concentration of sample. If we observe this equation, you will find that this equation can be used for determination of n value, determination of number of electrons involved in reaction. Similarly, here it is used for determination of diffusion coefficient, diffusion coefficient. Then it is utilized for determination of area of electrode, as well as concentration, as well as scan rate or voltage scan rate in the experiment. Therefore, here, along with the concentration of oxidant and reductant, Randle-Sevig equation is also utilized for determination of number of electrons involved in redox reaction. We also determine the diffusion coefficient of that oxidant or reductant. We determine the electrode area of that working electrode. We determine the voltage scan velocity for that experiment if we know the concentration of that particular species, and here all other parameters are known. Therefore, all other parameters are known. Any one parameter we can determine, that may be number of electron, diffusion coefficient, area of electrode, voltage scan rate, etc. by using Randle-Sevig equation. Therefore, here cyclic voltammetry is also important tool for determination of electrode area of the working electrode. Therefore, here this peak current is proportional to the area of electrode. Therefore, area of electrode can be determined by this cyclic voltammetry. Student, we discuss the next application of this cyclic voltammetry. Student, in addition to qualitative analysis and quantitative analysis, cyclic voltammetry is an important tool for identification of a redox reaction. By cyclic voltammetry, we can study the course of reversible reaction, irreversible reaction, and quasi-reversible reaction. Reversible reaction means the analyte is converted into product and product is converted back into the original analyte. In irreversible reaction, analyte is converted into the product, but product is not converted into the analyte. In quasi-reversible reaction, analyte is converted into product, but total product cannot be converted into original analyte. Such reactions are said to be quasi-reversible reaction. That means in this case reactions are not perfectly reversible, those are partly reversible. That means in first reaction, when analyte is converted into the product, part of the analyte, part of that product may be converted into another product, and therefore reaction is not perfectly reversible. Therefore, here the course of reversible reaction and irreversible reaction can be studied by this cyclic voltammetry. In cyclic voltammetry, during negative scan, analyte is reduced. That means here, suppose that is a OX plus Ne, it get converted into RET. This is a reaction taking place in a negative scan, and if in positive scan, analyte is reduced back. Analyte is oxidized back to its original form. That means here RED again converted into OX with loss of same electrons. Here, if the reaction is perfectly reversible, then the cathodic peak current and anodic peak current are exactly same. That means here cathodic peak current determines the concentration of the species that undergo reduction, and anodic peak current determines the concentration of that species which undergo oxidation. If cathodic peak current and anodic peak currents are identical, means concentration of oxidant and concentration of reductant are same, means the reaction is perfectly reversible. But when IPC is not equal to IPA, that means, or sometime IPC is greater than IPA. In this case, reaction is not perfectly reversible. That means whatever the cathodic peak current or magnitude of cathodic current is not equal to magnitude of anodic current, that means the total product is not converted into the analyte. Or sometime when cathodic peak current found to be more than anodic peak current, then also total product cannot be converted back into the original state. Therefore, such reactions are called as irreversible reaction, irreversible, or irreversible, or quasi reversible. Therefore, in a reversible reaction only, magnitude of cathodic current is equal to magnitude of anodic current. And if both magnitudes are not identical, then reactions are said to be irreversible and sometimes quasi-reversible. If we have a cathodic current, or if we have a current in first scan and we does not have a current in second scan, then reaction is irreversible. That means we obtain only this first cathodic current, we does not have a second wave. That means here product is not converted into the analyte. At that time reaction is irreversible. But when we have a cyclic voltammogram with less amount of the current in second scan, that indicates some of the product is get converted into reactant. That is OX plus Ne converted to RED, and RED is converted into another product which is not reactive at working electrode. Such reactions are said to be quasi-reversible reactions, in which we can say that those reactions are reversible, that observed as reversible, but those are not perfectly reversible, those are quasi-reversible. In quasi-reversible reaction, anodic peak current and cathodic peak current not exactly same. In irreversible reaction, either we have a cathodic peak current or anodic peak current, who does not have a both type of current in irreversible reaction. That means we does not convert that product into the original analyte. In this way, cyclic voltammetry is a very important tool to study the course of reversible reaction. Similarly, by means of this cyclic voltammetry, we can determine the N value of the reaction. That is, N value means number of electrons involved in redox. In a cyclic voltammetry, the EPC, that is cathodic peak potential, and EPA, anodic peak potential, are separated by a factor 57 millivolt. And this 57 millivolt means here from this point to this point we have this value, that is 57 millivolt, which is equal to 0.057 volt. Therefore here 57 millivolt, this value is very valuable, 57 millivolt. Here peak to peak separation for perfectly reversible reaction involving one electron is 57 millivolt. And if we have this difference less than 57 millivolt, then we can say more electrons are involved. Therefore here in this case, when 57 millivolt for a perfectly reversible reaction involving a single electron, and therefore here in this case, here peak to peak separation, that is mod of EPA minus EPC. The difference between anodic peak current and cathodic peak current is equal to 2.22 RT upon NF. Here R is gas constant, T is absolute temperature, N is number of electrons involved in redox reaction, F is Faraday's constant. This is called as delta EP. Delta EP is equal to, when we find out at 25 degrees centigrade, this value becomes here 0.057 upon N at 25 degrees centigrade or 298 degree Kelvin. Therefore, here peak to peak separation that gives us the value of N. Therefore, N is equal to 0.057 upon delta EP. If delta EP is equal to 0.057 volt, then N is equal to 1. And if delta EP is equal to 285 volt, then N is equal to 2, and so on. In this way, we can determine the N value or number of electrons involved in redox reaction by means of cyclic voltammetry using anodic peak potential and cathodic peak potential. That is the delta EP, which is equal to 0.057 upon N. And if delta EP is known, then N can be determined. These are the different applications of the cyclic voltammetry. Students, now we solve some numericals based on the applications on cyclic voltammetry. Number one is in cyclic voltammetry, voltammetric study of a redox reaction. N value is given equal to 2 during forward scan. The peak potential was at 0.368 volt, and during a reverse scan, the peak potential was at 0.319 volt. Was the reaction is reversible. That means here we have a cathodic peak potential and anodic peak potential. From this we have to determine whether that reaction is reversible or irreversible. We know that in cyclic voltammetry, peak to peak separation, that is delta EP, is given by this equation, that is mod of EPA minus EPC is equal to 2.22 RT upon NF, and here at 25 degrees centigrade delta EP is equal to 0.057 at 25 degrees centigrade. In this case, here n value is given to you, that is equal to 2. What is delta EP? If we subtract this value from this, then delta EP is equal to 0.368 minus 0.319 volt is equal to 0.057 upon 2. If delta EP in this case it is equal to 0.047, it is mod, that means a mod of this. 0.047 is equal to this divided by this means 0.0285 volt. That means delta EP is not matched with this N value or this ratio, and therefore reaction is irreversible. Reaction is irreversible. If we have this value equal to 0.047 here, then we can say that reaction is reversible. But here this value does not matches with each other, therefore reaction is irreversible. Similarly, cyclic voltammetry can be used for determination of N value of reaction. We can solve a problem. In a cyclic voltammetry study of a reduction of a vanadium, in cyclic voltammetry study of a reduction of analyte, reduction of vanadium to another vanadium, that is oxidant, here reductant. We have to find out how much electrons are involved in this reaction. In cyclic voltammetry study of reduction of vanadium, the anodic peak potential and the cathodic peak potential was observed at, that means potentials were observed at minus 1.436 volt and minus 1.496 volt respectively. Determine number of electrons, determine number of electrons involved in reaction. Here cathodic peak potential and anodic peak potential are given. That means in terms of cathodic peak potential, that is equal to 1.436 volt and anodic peak potential is 1.496 volt. Therefore, mod of this EPA minus EPC is equal to delta EP, and delta EP in this case equal to mod of minus 1.4, that is anodic peak is minus 1.436 volt, again minus of minus 1.496 volt, and which is equal to, here in this case this value equal to 0.058 volt at 25 degrees centigrade. And therefore here in this case we can find out N is equal to 0.057 divided by this 0.058. This value is equal to 0.9827 and which is approximately equal to 1. At least electron is not in decimal fraction. It is not in fraction, it is as a 1, 2 or 3 like this. Therefore, number of electron involved in this reaction is 1. That here it is a reversible reaction with 1 electron. We can find out here number of electron involved in redox reaction. Similarly, we can solve one problem based on the determination of area of electrode by using a cyclic voltammetry. In cyclic voltammetry, study of a oxidation of 1 millimole K4 FeCl6, N is equal to 1. Here K4 means ion present in +2 oxidation state. It is oxidized, means oxidation of this to K3 FeCl6, where number of electron involved are 1, has diffusion coefficient of 6.5 into 10 raised to minus 6 square centimeter per second in a 1 molar KCl solution, that is a supporting electrolyte. During its oxidation, during the oxidation of analyte by a voltage scan velocity of 100 millivolt per second, the anodic current was observed equal to 32 microampere. Determine electrode area. Therefore, here in this case we have to use Randles-Sevig equation, that is IPA is equal to 2.686 into 10 raised to 5 into N is 1 raised to 3 by 2 into D, that is 6.5 into 10 raised to minus 6 raised to half into mu. A we have to determine into mu scan rate, that is a 100 millivolt means 0.1 volt per second into concentration of analyte is 1 millimole. And if we solve this, we have here IP, that is 32.0. Therefore, A is equal to 32.0 microampere upon, here it is, this value is, by calculation this becomes 2.166 into 10 raised to 2, and which is equal to 14.737 into 10 raised to minus 2 square centimeter, and it is equal to 0.1477 square centimeter. In this way, cyclic voltammetry can be useful for determination of electrode area of working electrode. Student, this is all about the cyclic voltammetry, its analytical principle, its working and its different application, as well as we solve some problem based on these applications of cyclic voltammetry. Student, with this we stop here. Thanks for joining me. Wish you all the best. Keep learning. Happy learning.